Okay, well, there's the big note right there. U cross V is orthogonal to both U and V. So here's another interesting thing that's not that easy to prove, actually. It turns out that U, V, and U cross V form a right-hand system. So I'm not going to prove it, but I will draw you a picture as to what we mean by that. So let's say we have, you got to kind of imagine this is in 3D. It's going to kind of be like drawing the axes, but we don't have to have U and V be perpendicular. So let's say we have a vector U. Maybe it's kind of pointing out of the screen. Who knows? So there's U. And then let's say we have a vector V. These guys are not necessarily orthogonal. They don't have to be the same length. Okay? You can determine using this note and this idea as to which direction U cross V will point. Wait a minute, let me back up. Does everybody realize that there's two different we know that U cross V is perpendicular to both of those vectors, right? But there's two different ways that can happen. If you put the tail at where U and V meet, so we'll make U cross V red, then, you know, without any other information, you don't know if it points perpendicular in that direction to the plane formed by U and V. That's another way of thinking of it. Or if it points that direction, right? Well, you actually do know, because for UV and U cross V to be a right-hand system, it has to point in that direction. So the idea is that this is a right angle right here. I'm trying to give it perspective. That's why I'm not drawing it flat to look flat. So U cross V has to point in this direction. And it's, if you like the Homer Simpson version of the right-hand rule, then Homer's head is pointing in the direction of U cross V. And Homer's right arm is U, and his left arm is V, and that works great. And then the other explanation I tried to give the first day of class, and you guys looked at me like I was crazy. I should have saved it for this. So imagine you take your right, you got to use your right hand here. This won't work with your left hand. Imagine you take your right hand and curl it around U cross V. Then, first of all, the direction that you're curling your fingers, it's kind of like crossing U in the direction of V if you were actually you're not, but if you were actually pushing that vector, that's what would happen. The direction your thumb is pointing is the direction U cross V is going to go in.
Would V cross U be going negative?
Yeah, in fact, V cross U would point in the opposite direction. U cross V and V cross U, it's one of your first examples of multiplication that's not commutative. In fact, there's a note coming up on that. So, hey, guess what? You predicted the future right there. U cross V is equal to the opposite of V cross U. Because of that right-hand rule, basically. So when you cross it in the other direction, VU and V cross U have to form a right-hand system. And if you analyze it using a picture I just used, you'll see that it points in the other direction. What do you think you'll get if you cross U with the 0 vector, components all 0? The 0, is it going to be a vector or a scalar? A vector. So it'll be a vector. And by the way, if you're a vector in the plane and you want to take a cross product, you got to add on the third component of 0 to the vector in the plane. The cross product only works on space vectors. So U cross the 0 vector is 0. It turns out that U cross V is equal to the 0 vector if and only if U and V are scalar multiples. If and only if U and V are scalar multiples. If you've ever had any matrix theory as far as taking determinants, this will be pretty clear. So if you know that there's scalar multiples, so if U is equal to C times V, and you wrote out that determinant U cross V, or that cross product rather, then you have I, J, K. And then you could write, instead of writing it U1, U2, U3, you could write C times V1, C times V2, C times V3 for the components of U, because U is C times V, and V has components V1, V2, V3. And then if you play, and then for the third vector, it's just the components of V, V1, V2, V3. If you look at those submatrices and the subdeterminants, it's going to be pretty apparent that you get a 0 resulting. So let's see if we can not do the whole thing and start to believe it. What if I cross this guy out and this guy out to get the first component? Do you see that you get, when you take this determinant, you get C times V2, V3 minus C times V3, V2, or V2, V3, and you get 0. And it'll be true for the other ones as well. Is that a good enough, quick justification? Everybody believe that? Okay. It turns out that the magnitude U cross magnitude V, this is note number 6, and this is kind of a nice one. At least it comes in handy. It turns out that that's the magnitude U, magnitude V, times the sine of theta, which looks vaguely familiar. Kind of looks like that alternative form of the dot product, right? But it's not the same. It's that U dot V is equal to magnitude U, magnitude V, cosine theta. So not the same, but there's kind of a resemblance there, a family resemblance there. I'm not going to prove that one yet, the proof's in the book, but I will prove number 7 for you. For number 7, the magnitude, this is a huge idea too, believe it or not. The magnitude of U cross V is the area of a parallelogram formed with adjacent sides U and V. So that one's actually not too bad to show. Okay, so this will be like a little proof. Let me stretch this out a little bit more. There we go. That's what I want to do. So the idea is you could think of, say, this side as vector, I don't know, V, doesn't matter. And this side as vector, can't draw straight, which is why I always use the draw tool. I drew a red vector. There we go. Okay, so the purple guy is vector U. Do you remember the formula for the area of a parallelogram? A for area equals, just generically, if it has a length, a base, and a height, it is base times height. No, okay, I better not use that symbol. Base, little dot for multiplication times height. So the way I've drawn it, couldn't we call the length of the base the magnitude of U? Yeah. So the way I've drawn it here, we could call the length of the base, in other words, the length of the base, the length of the vector in purple would be the magnitude of my little half arrow suffering there. Okay, but then what's the height? Yeah, well, as you've done in trig, let's go ahead and prove that. As you've done in trig, tricky trig we call it, drop that perpendicular, right? The angle between U and V, you could call theta. And then if you think about it, that dashed yellow line there would be the height, right? The length of that would be the height. So we could use projections, but let's just use trig, right? So what would be the length of this opposite side to theta? Using the SO part of SOHCAHTOA, you could show that it's magnitude V times sine theta, and that's the whole proof, you guys. Does everybody believe that? Using right triangle trig? Okay. Then this height value right here then is magnitude V sine theta. Why is that the whole proof? What do we know from number 6? Yeah. Yeah, that equals magnitude U cross V, and that's what we were setting out to prove. Done. Okay? So that's kind of weird. If you have adjacent sides represented by vectors U and V, you can take the cross product, take the magnitude, and get the area.